Hey guys, how we doing? Mr. Patterson checking in with our first video for IB Math SL Chapter 24. Chapter 24 is all about continuous random variables, which is to distinguish itself from Chapter 23, which was about discrete random variables. Now, if you remember at the beginning of Chapter 23, we talked about the difference between discrete and continuous random variables. Discrete means countable, meaning that we can count the number of outcomes that a particular random variable can have. Whereas when we have continuous random variable, we say those are measurable. So we can measure, we can weigh, we can time, we can do anything like that. And what that means is that the random variable can take any value in a given interval. So if we look at this example here, it says a salmon breeder catches hundreds of adult fish and he records their weights in a frequency table. Now, if we look at these weights, 3 to 3.1 kilogram, 3.1 to 3.2, 3.2 to 3.3, etc. If we think about that, it might not surprise you to know that the weights of these salmons are not equally likely. Instead, they follow a curve that looks more like this, which you've seen before. It's referred to as a bell-shaped curve. All right. We will eventually learn to call this a normal distribution. But for purposes of what we're trying to understand right now, basically we're trying to look at this and say, well, what could these weights, what values could the weights take? Well, they could take any value in a given interval. So anywhere from 0 to I don't know what the maximum weight of a salmon. I don't know. But let's just say theoretically, or 10 kilograms, right? So it could be 3.723 kilograms. It could be 5.729 kilograms, whatever the case might be. Now, in order to answer questions about the weights of these kilograms here, they tell us the mean is 4.73 and the standard deviation is 0.53. And then it gives us this table here, or this diagram here. And you'll notice that there's a histogram with the smooth bell curve shape drawn on top of it. Now, in order to answer the questions underneath, we'd really need to think a little bit more about what normal distributions are. But for argument's sake, we could try to answer the questions a little bit. If it says the mean is 4.73 and the standard deviation is 0.53, well, that's quite a few standard deviations away from the mean. Is more than two standard deviations away. So for that reason, to get a salmon whose weight is greater than 6 kilograms is pretty unlikely because it's pretty far down the path here, uh, far from the mean, which is going to be the center of this distribution here. Between 4 and 6, well, that's going to take up the big chunk in the middle, so that's going to be a pretty likely outcome here. And then the questions for B, which find the weight where 90% weighed less than it. Well, 90% is going to be somewhere about here because that looks to be about 90%, giving about 10% left over in the tail here. So I don't know, maybe that's going to be like 5.5 or something like that. 25% way more than, okay? So maybe that's going to be about here, where I'm going to have 25% in this area and 75% in the area to the left. So maybe that's going to be about 5.2, something like that, all right? But again, these numbers that I'm coming up with here, you're not expected to be able to come up with these numbers just yet. I just know a little bit more about normal distributions, therefore I can answer these questions a little bit better. Well, let's take a step back. Let's focus more on just what continuous random variables are before we get to our bigger conversation on normal distributions. So what is a continuous random variable? It's a random variable that can be measured, okay? It can take any real value. And it says we use a function called a probability density function to define the probability distribution. So the idea that a curve could define what the probabilities will be for this for these continuous random variables is something that we're going to be spending quite a bit of time with. Now, don't get worried when you look at this slide here. We're talking about integration, which we've been away from calculus for a little bit here, but we're talking about integration. Now, if I integrate the f of x, the function that defines the probability, from a to b, and A is down here and B is up here, Well, that is going to be 1 because basically what we're saying is that the area underneath the curve between 2 points is the probability of those particular outcomes. And if we're talking about area underneath the curve, we're talking integration there. So that makes sense there. Now this one is saying the area underneath the curve from A to B is 1 because, well, that's the whole area underneath the curve. But if I'm looking for the probability that x is between C and D, then I'm going to integrate from C to D. And whatever this area is here would be the probability of that particular outcome. Now, again, you don't have to worry about this. We're not doing calculus to find these probabilities, but if you see this down the road in another math course, this might be the way that you do it. Now, when we go to interpret here, we're trying to interpret, we just need to make sure that when we find these areas, and again, we're not going to be doing it using calculus, we're going to be using other means. We just need to make sure we're answering our question in terms of the correct units that we have. So now let's get into our first section, the normal distribution, 24a. We're going to talk about why normal distributions are important, and we're going to talk about how to apply them, and we're going to find probabilities using something referred to as the empirical rule. So what is a normal distribution? The normal distribution is something that comes up quite often in the natural world. So physical attributes such as of a population such as height, weight, and arm length. So height, for instance, okay, let's just take for argument adult males. If I were to tell you the adult male average height is 5'10", you probably wouldn't be surprised by that. So that means that a lot of people will follow heights very close to 5'10", maybe 5'9", 5'11", maybe even 5'8" or 6 foot. But the number of people whose heights are far away from that, say 6'4", 6'5", or even 5'4", 5'3", those people are very unlikely, right? So if you could kind of picture that normal distribution curve that we saw previously in this video, you can understand that most of the people are going to be about 5'10". Some people are going to be a little bit farther away, and even fewer people are going to be very far away from that. Crop yields. From year to year, you're going to get different results from planting your corn, your wheat, your whatever. But in general, you're going to get about the same amount, and then you'll get a little bit less, a little bit more in most years. Some years you'll get quite a bit far away from there, and even other years you'll get, what are considered to be outlier values there, right? Scores for tests taken by a large population. Most test scores are going to follow normal distributions, right? Most people get somewhere around whatever that mean happens to be. Maybe it's about a 75, maybe it's about an 80. There's a few people who do a little bit better, a little bit worse, but in general, they're more concentrated near that mean, right? Now, how do they arise? They arise naturally, right? So genetics, different times flowers are fertilized, different amounts of sunlight reaching the leaves and fruits, different weather conditions. These are all uh, variables that are going to affect the whatever it is we're measuring here. In this case, we're talking about the weight of the oranges from an orange tree. All right. Now again, here we see some high level math, and it's not something we need to worry about for this particular course. It says here that f of x equals, and then we see this big heavy formula. This big heavy formula is the normal distribution. It is an actual curve that you could graph in your graphing calculator, and you could see that bell-shaped curve coming into play, right? Now, just a couple of variables in here that we need to make sure we're clear about. The variables that we have are mu up here, the Greek letter mu, that's for mean, and this lowercase sigma, which is the population standard deviation. That sigma appears twice here, right? We see other letters here, right? We see pi and we see e, but those are constants that we're aware of. Now, just like we wrote our notation in chapter 23 with binomial distributions, we also have notation for the normal distribution. This one here says x is distributed as a normal distribution with mean mu, and the other variable that we put in here is the variance. Now, I just got done telling you sigma is the standard deviation, so therefore sigma squared is the variance, right? Now, what does it look like? Well, here's what we know it looks like. We know it's going to be centered at the mean. The height here we don't need to be concerned too much about this, but obviously that's going to be the highest point on the graph. Um, and basically, the general idea here is that this curve will go on forever in the negative direction and forever in the positive direction as well. But because this curve is asymptotic with the x-axis, when we get really far away from the mean, the probability of those outcomes is very, very small, practically insignificant. All right. So if we went a little bit further, we could talk about finding the first derivative and understanding how that helps us find where the mean is, and the second derivative and finding that's where the standard deviation is. But that's not really important to what we need to do. What we need to really focus on here is what's referred to as the empirical rule, or the 68, 95, 99.7% rule. And what this does is it allows us to take this normal distribution, break it up into different segments here. Now let's just go through it here. The mean is in the middle. We already talked about that. When I see this here, mu plus sigma, this refers to the point where we are one standard deviation above the mean. And this up here is saying that 34.13% of the values are going to be in that interval between the mean and one standard deviation above the mean. Similarly, because it is symmetrical, the proportion of observations, or the percent of observations from one standard deviation below the mean to the mean, is also 34.13. This is one standard deviation above to two standard deviations above, and that is 13.59%. Two standard deviations above to three standard deviations above is 2.15%. And there's only 0.13% of observations that are more than three standard deviations above the mean, and vice versa, below the mean as well. So it's referred to the 68, 95, 99.7% rule because if you added these two percentages together, that's about 68%. And if I added 13.59, 34.13, 34.13, and 13.59 again, that's the percent of observations within two standard deviations from the mean. So within one standard deviation of the mean, about 68%. Within two standard deviations of the mean, about 95%. And then if I went and added in these 2.15s on both sides, I'd get about to 99.7%. You can see a little bit more accuracy in the numbers down here at the bottom of the slide. 68.26, 95.44, and 99.74%. All right, so let's put that into practice. Says the chest measurements of 18-year-old male footballers are normally distributed with a mean of 95 and a standard deviation of 8. So 95 is going to be in the middle. And if I go one standard deviation above, that's going to take me up to 103 centimeters. So it says find the percent of footballers with chest measurements between 87 and 103, and then 103 to 111. So we'll come back and look at B and C in a second. Here's A. So here's my drawing. Starts at 95. I go up to 103, 111. How do I get there? I'm adding 8 each time because 8 is the standard deviation. And I can do the same thing in the opposite direction. Subtract 8, I get to 87. Subtract 8, I get to 79. So this particular question in A says 87 to 103. 87, one standard deviation below the mean. 103, one standard deviation above the mean. So it's like I'm adding the 34.13 and 34.13, and I get about 68.3%. When in A double I, it says between 103 and 111. 103, 111, I'm literally just going to take the value from the curve we saw before, and that's one standard deviation above to two standard deviations above. So the answer to A double I is just going to be that 13.6%. Now B says find the probability that is between 87 and 111. Okay, 87 was here, and 111 is here. So I'm shading in this area in the middle, and I'm just going to add those percentages together. When I add them together, I get about 81.9%. Let's take a look at question C. C says find the value K such that approximately 16% of chest measurements are below K. All right, so if I look at this one here, I want 16% below it. Well, if I go back to the original graph that we showed where the percentages are, I see 0.13%, 2.15%, so that's about 2.3. And here's 13.59%, And if I add that together, that's pretty much 16%. I mean, it's slightly less, but not too big a deal. So where are we at this point? We're talking about one standard deviation below the mean, and I have 16% of the observations below it. So to answer this question here, find the value of k. K is just going to be one standard deviation below the mean, so it's 95 minus 8, or 87 centimeters. All right, so this is going to take a little practice for you to understand, but the general idea is that you want to draw these normal distributions, label the values from, the mean, and then out three standard deviations in either directions, and you're just using the percentages that we talked about here. So I'd like you to try to work on that. Page 634, 1 to 13 odd, and let me know if you have any questions that I can go over them for you. Have a great day and talk to you guys soon.